Hello guys, welcome to another video on physics revision for JEE Advanced. Today, before solving numerical questions, I would like to focus on a very important theory portion which we generally do not focus much in our class because of time constraint. That is Maxwell-Boltzmann velocity and speed distribution function. Actually, this function talks about statistical physics. So when Maxwell and Boltzmann they represented this function, people did not believe that it is a part of physics, because up till then physics was only about certainty, right? It was not about probability. But when you talk about millions and millions of gas molecules present in a chamber, you cannot talk about certainty, right? You have to take some statistical data on which you can conclude few macroscopic property of the gas. So that was done by Maxwell and Boltzmann. Now, most of us know that Maxwell-Boltzmann has a velocity distribution graph that we generally study in our reference book. But you should also know, and more importantly, that this Maxwell-Boltzmann not only gave us a speed distribution graph of the gas molecules, but they also gave us the velocity distribution graph. So I will, in this particular lecture, try to brief you about the application of this distribution function, not on the derivation part. Definitely, the derivation needs a very intense calculation that is not in our scope of mathematics. So we will skip the derivation portion, and we will directly jump to the formula and how to apply those formula in numerical questions that we will discuss with the help of few numericals taken from Irodov and Pathfinder book or some other Olympiad level questions. Okay, so being said that, first we will talk about the velocity distribution function. Let us assume that in a gas sample, it may be a huge volume, or it may be a very small volume. Whatever volume you take, the gas molecules are isotropic. So you can say that inside this volume, suppose there are so many gas molecules moving here and there with different velocities in different directions. Now, if you want to take only the x component of all those velocities, only the x component of all those velocities in any given volume, then you will find that the velocity in x-axis ranges from minus infinity to plus infinity. So Maxwell's velocity distribution graph tells us that what fraction of this total number of molecules are moving with a particular velocity range from Vx to Vx plus dVx. So if the function looks something like this, here and here, then you can say that if this is the fraction in this y-axis, I am drawing the fraction, then this is a small area, I will assume, from Vx to Vx plus dVx. This is dVx. So if I say that how many number of molecules are present that are moving with this particular velocity Vx to Vx plus dVx, then Maxwell's Boltzmann velocity distribution curve will help you to find that number. How? This number can be found by multiplying the total number of molecules present in that particular volume into the fraction which is given by the function f of Vx into dVx. Right? So this is the fraction of the total number of molecules that are moving with a particular velocity range of Vx to Vx plus dVx. Here I have written the function of f of Vx, and it is not mandatory to remember this function or memorize this. It is not needed anywhere in any mathematical calculations or any numerical examples. But we will try to understand how to apply this particular formula. So here you can say that minus infinity to plus infinity f of Vx dVx equal to 1, obviously, because all the molecules that are moving in x direction has a velocity range from minus to plus infinity. If I only talk about the positive x-axis molecules, then I will integrate it from 0 to infinity, and that fraction is half. The reason behind is that the nature of the gas molecules are isotropic in nature. So the number of gas molecules are moving from 0 to infinity is the same number of gas molecules that are moving from 0 to minus infinity velocities. Right? So minus x-axis and plus x-axis, they are equally probable. So that is why the fraction is half. Now if I ask you what is the mean speed in that particular direction, so mean speed means I can say that all the gas molecules that are present in that small rectangle or lying in between Vx to Vx plus dVx, I will say that their speed is Vx. Their speed is Vx. So what is the number of gas molecules with this speed Vx? I can say I will multiply this with this one. This is the number of gas molecules that are moving with Vx. So if I multiply this with the number of gas molecules that are moving with Vx, which is this one, and if I integrate it and if I divide this with the total number of gas molecule present, then I should find the average value of the x-axis speed of the gas molecules. Right? So n gets cancelled out, and you will find that this is integral of minus infinity to plus infinity. I am talking about the total domain of the gas molecules, f of Vx into mod of Vx dVx, which is 2 times of 0 to infinity f of Vx mod of Vx dVx, and the value you should remember is root over of 2 kt by pi m. Similarly, if I talk about RMS speed, instead of mod of Vx, I will apply Vx square. And from minus infinity to plus infinity, it is the same as 2 times of 0 to infinity, and the value is root over of kt by m. Similar is the case for Vy and Vz. So I have not written those formula for Vy and Vz. But for Vx, for any particular direction, you should remember these two formula. Right? The second formula is easy to remember. I will tell you why. But the first formula is root 2 kt by pi m. You have to remember. Now jump to the speed distribution function. Now speed distribution, when I am talking about, it does not have any particular direction. It's always a magnitude, and it starts from 0 to infinity. Right? So if I say that all the gas molecules, they have a particular speeds, and the speed range is from 0 to infinity. Right? Now there is one interesting thing, that if I ask you that this is the speed distribution function f of v, and similar way, if I say that this particular molecule is moving with a velocity speed of v, can you tell me that what is the number of molecules that is moving with velocity v? The answer to this question is 0, as the Maxwell-Boltzmann velocity or speed distribution graph These functions talks about the number of molecules present within a velocity range. The number of molecules moving with a particular velocity or exact velocity is 0. The probability is very small. So we can say that the number of molecules moving with a particular velocity is 0. So similarly, if I have to find the number of molecules moving with a velocity or speed from v to v plus dv, v to v plus dv, then I can take help of this Maxwell-Boltzmann speed distribution function, and I can say that this is the total number of molecule multiplied by the fraction which is f of v into dv. That is the total number of molecules moving with the speed range of v to v plus dv. This is the function. Again, you do not need to remember this function, but you should remember that what are the mean and the RMS value of that function. As I have discussed the mean value in one direction, similarly mean speed in all the direction is f of v mod v into dv. That should be dv. Yes, and that value is root over of 8 kt by pi m, and RMS value in all direction is root over of 3 kt by m. That we all know, right? It can be also written as 3 RT by capital M, right? Molar mass. Capital M is the molar mass, or small m is the molecular mass, mass of one molecule here, right? So you can see a relation between RMS speed in one direction and RMS speed in all the direction. The relation is very obvious, that V square is equal to V x square plus y square plus z square. And we all know that these molecules are isotropic in nature. So the average value of x square, y square and z square all are same, and that is root kt by m. So if I square them, kt by m plus kt by m plus kt by m, that is equal to 3 kt by m, which is v square, the average value of v square, right? So you should remember that these all are same, and this is the average value of v in a particular direction, and this is the average value of v, or the speed in all the directions taken together. So I hope you have understood this Maxwell-Boltzmann distribution function, how they are used, and you have got a good idea of how we can apply these functions to find the mean and RMS speeds. Again, before going to any question, I will give you a actual derivation of the pressure of a gas. So let me try to do this expression with the help of the Maxwell's function, right? So let us try to understand this derivation of pressure. Let us take a box where gases are kept, and I have taken this particular direction to be my x-axis, and this is a wall with cross-section area A, and I have taken a small volume. This is a suppose unit volume, you can say, right? This is a unit volume where the number of molecules are small n. So small n is the number of molecules per unit volume, and mass of each molecule is m. Now the number of molecules that are moving with Vx to Vx plus dVx velocity is n into f of Vx dVx. Look, I am here only interested in number of molecules that are moving along x-axis, because the number of molecules that are moving along y or z-axis are not going to collide with this particular one, right? So the number of molecules that are colliding with the right wall per second will be the molecules lying within the volume A into Vx. I hope you can understand this, because if this is the area, Suppose this is the area, and if I say that a particular gas molecules, or not a particular gas molecule, number of gas molecules, those who are moving with a velocity Vx. Velocity Vx means the velocity range is there, Vx to d Vx plus Vx. You can understand that in 1 second only this much number of gas molecules which are lying inside this volume are going to hit this wall, right? What is this length? This length is obviously Vx. In 1 second, the gas molecules, those gas molecules which are inside this volume can only hit it. The gas molecules which are out of this volume cannot hit it, right? So the number of the volume is A into Vx. So what is the total number of molecules that are moving with a velocity range Vx to Vx plus dVx, and that are inside this volume is A into Vx multiplied by this number. But you should remember that here I have taken the velocity from Vx to Vx plus dVx. I have not mentioned whether this velocity are along positive or negative x-axis, because some molecules will also move in negative x-axis, and those are not going to collide with this vertical wall, right? Okay, so when I will integrate it, remember I will only integrate from 0 to infinity, not from minus infinity to plus infinity, because 0 to minus infinity means particles are moving along negative x-axis, that are not going to collide with this one. Okay, so what I have done here, I have said that if I multiply this volume with this number, then I will get the total number of molecules that are moving with a velocity range of Vx to Vx plus dVx, and inside this volume those are going to hit this particular wall in 1 second. And we all know that in every collision the change in momentum of one molecule is 2m Vx. So the total change in momentum is 2m Vx multiplied by this number, right? And that is the force, because change in momentum per second is the force, and average force on the molecules is the same average force on the wall. And when I integrate, as I have mentioned, that I will not take minus, so from 0 to minus infinity velocities, I will only take 0 to infinity velocities. So I take out 2m into n into a outside, and the result that I get inside the integration should be well known to you, because this is integral of 0 to infinity f of vx square, if you and into dvx. If you recall, in the last slide we have mentioned this as the RMS value in one direction, that is average of Vx square, and I have mentioned that average of Vx square is equal to average of Vy square is equal to average of Vz square, and that is equal to 1/3 of average of V square, or that is 1/3 of Vrms square. So now I can substitute it here, and I can find that it is mn a by 3 into Vrms square. Now m into n is the mass into number of molecules, so it is the total mass of the n is the number of molecules per unit volume. So if I say it is capital N by V, capital N is the total number of molecules, then capital N into M is the total mass of the gas, divided by volume is the density, and if I divide force by area, then I can say it is a pressure. So that is 1/3 rho Vrms square. That is a correct proof of this pressure of a gas, I think, because I have taken this Maxwell's distribution function. Instead of assuming that one molecule is moving with Vx, that has no meaning, I think, because there is no molecule that will move with Vx. According to Maxwell distribution, there is no molecule that is moving with particular velocity Vx. The number of molecules moving with Vx to dVx, that is defined. That I have taken here into consideration in this proof. Now there is a question. This question says, how will the rate of collisions of rigid diatomic molecules against the vessel's wall change if gas is expanded adiabatically eta times? This question based on the same principle that we have just used by using Maxwell's velocity or speed distribution function. So I will suggest you to just give it a try for a few minutes and then again come back to see the solution. So guys, I think that you have given it a good try. Let us now jump to the solution page of this particular question. In order to find the solution of this question, first I have to understand what is this rate of collision and on which factor this rate of collision with a particular wall depends. So I have written lots of things here. You can understand from this diagram first. Suppose this is the vertical wall. I have taken a unit area and I have to find how many number of molecules are going to collide per second with that particular unit area. I have taken any unit volume present here, right? Any unit volume, and the derivation goes like this. Inside that unit volume, let us assume that small n is the number of molecules, and out of that the number of molecules that are moving with a velocity Vx to Vx plus dVx, as I have to only consider the x directions molecules, so it is n into f of Vx into dVx. Now in 1 second we should only consider the number of molecules inside the volume, that is, if you consider this is the volume inside which the gas molecules can only hit in 1 second, and that is the Vx multiplied by the area, which is only 1, right? And the time is also 1. So I can say that inside this Vx unit volume, whatever may be the number of gas molecules that are traveling along positive x-axis with a velocity Vx to Vx plus dVx, that are going to collide with this particular wall, right? So Vx in this case varies from 0 to plus infinity, right? 0 to plus infinity only. So the number of collisions will be n multiplied by 0 to infinity f of Vx into Vx dVx, right? As I am saying that the direction is only one direction, and now so it does not make any sense to put the vector sign, because I know that it is moving in positive x-axis only, right? So I can say that the number of collisions per unit area per second will be 0 to infinity this integration, and you should remember that this integration talks about the average speed in one direction, which was root over of 2 kt by m, right? And it is not from minus infinity to plus infinity. 0 to infinity is half of the average value, right? So I have written this integration as half into n into root 2 kt by m, right? And we know that average speed in all the directions taken together is root over 8 kt by m. So if I slightly modify it, instead of 1 by 2, if I take 1 by 4, then 2 will come inside the under root and it will become 8 kt by m. So it is 1 by 4 into n into mod of v, average of that, average of the speed in all directions taken together. What is n here? N is the number of molecules per unit volume. Remember that, very important. N is number of molecules per unit volume. Now come to the question. This particular question says that it's expanded adiabatically and its volume expanded eta times, right? So again I can say that the this number of collisions per second per unit area, this depends on n by v and root over of temperature, right? So for a particular vessel where the number of molecules remain constant, then it is proportional to root T by V. Now in adiabatic condition, we know that T into V power gamma minus 1 is constant. So T2 by T1, I can say V1 by V2 into gamma minus 1 to the power gamma minus 1, which is 1 by eta to the power gamma minus 1. So R2 by R1, which I have to check what is the value, it's V1 by V2. From here I can write it V1 by V inversely proportional to V. So V1 by V2 root over of T2 by T1. So that is 1 by eta into root over of eta to the power minus of gamma minus 1. As a diatomic gas is there, so gamma is 7 by 5. Putting the value of gamma, I got the answer to be eta to the power minus 6 by 5. So that should be the answer of this question. Now this lecture doesn't end here. I have 2 more questions to solve on the similar principle that I have used here, discussed in this particular lecture. But I want you to try those questions by yourself, and then in the next lecture I will make a video of the solution of those questions. Okay, so you tried solving this question. I have taken this from the Pathfinder book. This is also based on the same concept that we have just discussed in this lecture. And after this question, you try solving this one. This one I have taken from the book of Irodov. This is also a question on velocity distribution. So you try solving this one. This is mv square, right? It is e to the power minus mv square by 2 kt. So it has given you a function, a velocity function, and with this velocity function, you have to answer these 2 questions. So you try these questions by yourself. See you in the next video with the solution of these 2 questions.